In this video, we want to consider just two simple examples to introduce our concept of encapsulation. Suppose that we just have an ethylene molecule. So, two carbon atoms linked together by a sigma bond and a pi bond, and this carbon, of course, has two hydrogens attached to it. And both carbons are sp2 hybridized. So this would be an sp2 orbital, an sp2 orbital, an sp2 orbital. Then it has a single electron in the pi orbital for the pi bond, the double bond that forms between those two carbons. And again, we've gone over that in a lot greater detail back in the beginning part of the video series. Now suppose that ethylene loses a proton. Then we would have, let's say this one is gone. It leaves the electron behind, but the proton is gone. So this carbon would have an unshared electron pair, and those would be sp2 electrons. Now, the likelihood of this happening is not very high if we have ethylene to give to function as an acid. The pKa is about 42. So this is highly unlikely. But suppose that instead of ethylene, suppose we have acetylene. Now both carbons are sp hybridized, and we have two pi bonds. So for each carbon then there is a p orbital above and below the plane that overlap, something like this, and each one donates an electron to where they overlap. And then there's another p orbital going into and out of the plane, and that would have also a pair of pi electrons, one from each carbon. So these two carbon atoms are sort of surrounded in a cylinder of negative charge. And then this would be the sigma bond between carbon, and the other sigma bond, well, it would be a sigma S bond between carbon and hydrogen here and here. The point is that for the sigma bonds, they are 180 degrees apart, like this. Now, if this lost a proton, say this one, then we would have a pair of sp electrons here. This was an sp orbital. Just drawing the single orbital now. We have an sp and an sp, and then another sp orbital that overlaps with hydrogen. sp orbitals are 180 degrees apart, here and here, and then here and here. And then here we imagine the hydrogen atom leaving an electron behind. So there was two electrons being shared here. Now there's just two electrons and nothing to share it with because the proton left. So you would have this lone electron sp pair. But notice where it's at. it's right here at the end of the molecule. So the two carbons are sort of surrounded by this cylinder of negative charge from the double pi bonds. Then at one end, it's also is surrounded by negative charge. So it's encapsulated at one end. And that evidently helps to stabilize, because here then for acetylene, minus H plus to form the anion. Well, this has a negative charge. There's no hydrogen atom here. We lost the proton, so we have this instead. The proton goes away. Well, now the pKa for this reaction is not very high. It's still like 25. But notice now then that acetylene, its pKa is 25 compared to ethylene, the pKa is 42. So acetylene is about 10 to the 25 times more acidic than ethylene. And that is, when we form ethylene, we have this sp2 electron pair. When we do it with acetylene, we have this lone sp electron pair at one end of the molecule, kind of sealing it off, if you will. It's already surrounded by a tube, so to speak, of electrons from the double pi bond, and now we have another cloud of electrons at either end of the atom. And that's the encapsulation effect. Let's just take one more example here to sort of demonstrate this principle of encapsulation. Let's take this compound, a double bond between carbon and nitrogen. Like this, and then we have this. Now here, this has a lone electron pair, and that's an sp2 electron. These are all sp2 hybridized, both the nitrogen and the carbon. So if we lose a proton, say from here, so we have this, it has a negative charge because it lost a proton, and we'll have an unpaired sp2 electrons. Well, the pKa for this is about 30. Again, not an acidic compound, obviously. But now let's compare that, say, to cyanide. Cyanide looks like this. A triple bond between carbon and nitrogen, has a hydrogen attached to it. Now, here, the nitrogen, the sp hybridized nitrogen, it has a lone pair of sp electrons. Maybe we haven't drawn nitrogen before in a triple bond, so let's just see why this is so. Here is the molecular orbital diagram, as we've seen many times now for nitrogen. 2s orbital, the p orbitals, and now we form one s atomic orbital merges with one p atomic orbital to give us two energy equivalent sp molecular orbitals. Remember the geometry, they're 180 degrees apart. And then we have two unhybridized p electrons. So the nitrogen has an sp orbital, and then another has a single electron, and then another sp orbital that has the lone electron pair. And that's what we're showing here in the Lewis diagram. Here would be the pi bonds, and then the sigma bond with nitrogen formed by overlapping sp orbital from nitrogen, and there'd be an sp orbital also from carbon overlapping to form that single sigma bond. But here then, look what we have for cyanide. Carbon and nitrogen have this double bond, the double pi bond. So again, imagine here is carbon with a p orbital above and below, and then for nitrogen, a p orbital above and below. They overlap. Each has an electron that they share to form a pi bond. Nitrogen also has now the lone electron sp bonds. And then there is another pi bond, another pi orbital overlapping between carbon and nitrogen that goes into and out of the plane. So here for cyanide, again, we have the carbon and the nitrogen are surrounded by a cylinder of negative charge from the delocalized electrons, not the delocalized electrons, because these orbitals are overlapping, but here we have it here and then also into and out of the plane. So it's like surrounded by a cylinder of negative charge, plus we have these lone electron pairs on this end of the electron, or this end of the molecule. Then we have the carbon bonded to hydrogen, and again, the carbon is sp hybridized, so for carbon it's like this for its single bonds, sp orbital that overlaps with the sp orbital of nitrogen, then 180 degrees apart, an sp orbital that overlaps with the s orbital of hydrogen. Well now, if this loses the proton, there's a pair of electrons being shared here. But now, if the cyanide if it loses that proton, then we have this. With an sp pair of electrons at both ends. So now both ends of the molecule are encapsulated. And in this case, the pKa is about 9.2. So we compare it to this compound. There is no encapsulation. This is not acidic. That's a pKa of 30. But compare that now to cyanide, where we have this triple bond. One end is already encapsulated. If we can get rid of this proton, then this end of the molecule is also encapsulated. As we show here, sp electrons at both ends. Now the pKa is 9.2. Again, a substantial difference, and at least part of that effect, again, is attributed to this so-called encapsulation phenomenon. And in the next two videos, we'll try to have some simple examples where we have resonance occurring together with encapsulation. But that'll be it for this video then. You don't read a whole lot in textbooks about encapsulation, but as you can see, it is relevant. And again, we'll try to provide a couple more of examples now where encapsulation and resonance can occur together in the same molecules. Reminder here that the playlist for all the videos is at the website digital-university.org.